Hello, this is Jim, W9JUG, with part 1 of circuit analysis. For this episode, we have a circuit here containing an 84 volt battery and a 21 volt battery, 3 ohm resistor, 6 ohm resistor, and a 12 ohm resistor. Now this circuit cannot be calculated or solved by conventional Ohm's law techniques, so we use some advanced network techniques called loop equations, and this will help us to solve this particular circuit. Because of the influence of the two voltage sources, we only had one voltage source, we could solve the circuit quite easily, but now we have two voltage sources. That complicates the problem. So we start off by using Kirchhoff's voltage law, which states the voltage drops, in this case is 6 ohm, and in this case is 12 ohm, those are drops, plus the source must equal 0. Okay? So we have what we call loop number 1. So we simply write a simple equation to document that. Loop 1 over here. So the two currents, one from this 21 volt side and the 84 volt side combined, so it's I1 plus I2 as far as the 6 ohm. So it's minus 6 times the quantity I1 plus I2. Minus 12 I1, that is the voltage drop across the 12 ohm, plus 84, the source, is equal to 0. Again, Kirchhoff's voltage law. Okay? We combine the two I1 terms, so it's minus 18 I1, okay, minus 6 I2, plus 84 is equal to 0. Okay? For convenience now, we can get the 84 term over on the other side of the equation by adding a positive 84 to both sides of the equation. That makes this a positive 84 here. Okay? And, okay. Alright, to get all positive terms, we simply go ahead and multiply by a minus 1. That gives us plus 18 I1 plus 6 I2 is equal to 84. This is the final form of loop equation number 1. The whole key here, it can be solved otherwise, by other methods, but we want all positive values to work with. Loop 2 is done the same way. Again, Kirchhoff's voltage law, the voltage drops, alright, plus the source must equal 0. So we write that equation quite simply like before, but this time we have to include the minus 3I2. Alright, the 3 ohm resistor here is equal to 0. We combine terms as shown here. Okay? And we come up with minus 6I1 minus 9I2 equals a minus 21. Okay? Since we want all positive values, we'll just multiply through by a minus 1. We get 6I1 plus 9I2 equals a plus 21. That is the loop number 2 equation. To solve the problem, we now got to combine loop 1 and like loop 2. We do that over here by substituting loop 1 again. This loop 1. And here's loop 2. It's previously developed. Alright, but we find that if we want to combine those, we have two unknowns. So we might just go ahead and drop the I2 term out by dividing by positive 1.5. But that does, we divide 6 by 1.5, that's 4. Divide 9 by 1.5, that's 6. We substitute this equation, loop modified, in this base equation down here, and we see that the two I2 terms drop out, and we simply subtract. 14I1 is equal to 70. Okay, 84 minus 14 is 70. So I1 is 5 amps. Now that is the solution. We go back up and take a look at the circuit. That's 5 amps flowing through this resistor. We now know that the direction is minus to plus, and it's actually really 5 amps. That is the real current. From here we can then solve the complete circuit quite easily. Alright? That we will do in part 2. Now reviewing again, the whole secret behind these loop equations and this method of solving a complex circuit is Kirchhoff's voltage law, and that's the application where the voltage drops plus the voltage rise, in this case 84 volts, is equal to 0. That is shown here. Now through the 6 ohm, we have both loop currents, I1 and I2. So that's why we say a minus 6 times the quantity, I1 plus I2. Alright? Minus 12I1 plus 84, as you see here. Alright? And the other part of it is to want to point out is regardless of how you do it, right, it'll all come out. But it's much easier to handle in the final analysis by positive values. So multiplying by a minus 1, a minus times a minus is a plus. Okay? We change these to positive values, 84. Okay? Now, on this side, it's the same thing. We start here and go around. The voltage drops plus the source should be equal to 0. So we see that in loop 2 equation. We use the same process as before. Here we come down here where we have all these minuses, so we multiply by a minus 1, and that cancels the negatives out and becomes all positive values. Now the next problem, that's where the rub is, as they call it, as they come down here, is to modify the bottom equation, because we have 2 unknowns here. Alright, so an easy way to do this is to cancel one of these out. Now that'd be easy to do by modifying loop 2. If we divide by 1.5, the 6 becomes 4I1. If we divide by 1.5, 9 divided by 1.5, it comes out to 6. And we divide the 21 by 5, and that comes out to 14. Now we take the modified equation and we plug it in down here. And we see that the 2I2 terms cancel. So the problem becomes very easy to solve. Okay, 18 minus 4 is 14. This becomes 70. Alright, 84 minus 14. So it's just simply we divide both sides by 41, by 14 in this case. So I1 is equal to 5 amps. Now that is the real current that's flowing through this resistor. Now part 2 will go through how to finish the circuit off and determine what the real values for the 6 ohm and the 3 ohm are, and prove that everything is correct as we've gone through these loop equations. Hope you enjoyed this session. This is the end of part 1. Thank you for watching.